1D, the backward-Kolmogorov equation becomes trivially this one. Now it is immediate to show what qualitatively we were stating about the exponential stationarity of the commuter within the metastable state. The way to do that is simply to bring terms on the other side of this equation, and remember that the derivative of a logarithm of q is q prime over q. So if I do this, I get this, right? So if I do that, I get that derivative of logarithm of q prime is equal to beta derivative of u. And if you think about this, this essentially means that, after integrating both sides and taking the logarithm, it essentially means that q prime times the Boltzmann distribution. So let me write it this way. From this equation, it is immediate to show that the q prime of x times the Boltzmann distribution is a constant. Or stated differently, or stated differently, that q prime of x is a constant that depends on the boundary conditions divided by the Boltzmann factor. P of x is constant, possibly different one, of course. Now, clearly, wherever the probability is large or exponentially large, like inside the basins, the derivative of q is exponentially small. So what this actually means is that if I were to draw the commuter for a reaction like this, and I have shows the wrong axis. If I were to draw the commuter for a reaction like this, I would have like XA, XB, let's call this XO. I will get like stationary all the way to XA. Well, sorry, drawing this wrong. XA, XO, XB. So the commuter here would be 0 until XA. Now let's consider this to be, the region defining the intermediate state. So it would sort of grow into here, become stationary here, grow into this and become 1. So the stationarity of the commuter is actually a good sign of presence of metastability. You can even think, if you were able to compute a commuter, this would be a nice way to identify where metastable states are. Just look around where wherever the commuter is exponentially stationary. Okay, so that's an interesting property of the commuter, but that's not all. Let's now turn. Thank you. That's it. That was my son handed me this for my hair. Thanks. Let's continue and go back now to the problem of calculating the transition path density and the transition path current. Now let's consider first the transition path density. Now remember, the transition path density is the probability of observing a transition path visiting the point x. Now, if you know a little bit of probability theory, you know that when you have probability of disjoint conditions, then you can multiply that, right? The two things, the probability of being female and blue-eyed is just 1/2 times the probability of being blue-eyed, if the probability of being female is 1/2, which is not exactly 1/2. I learned from population scientists, for human at least. Which means the probability that in an equilibrium trajectory I visit point X along a reactive trajectories is the probability that I in equilibrium visit X, the Boltzmann distribution, times the probability that I'm reactive. Now, what means to be reactive when I visit X? It means the probability that I'm reactive that I visit X, it means that if I shoot a trajectory from X I get a relationship like this. This is Q plus, Q minus. And there's, of course, a normalization constant. Why is it so? Well, it is easy to see that, by microscopic reversibility, this is a point, the probability that the point X was reached coming from the reactants, and then from X I leave to the product. So that the product of the two, Q plus and Q minus, is simply the probability of being reactive while crossing X. And the combination of the two will give me my transition path probability, the probability that an equilibrium ergodic trajectory visits X while being reactive. So what we discovered here is something quite important, that if I knew the commuter by ideally by solving the backward Kolmogorov equation, then all I need to know to get the transition path density is that ingredient plus the Boltzmann. So in some sense, I'm minimally extending the Boltzmann theory to get non-equilibrium physics. The normalization here is obviously normalized over the transition region and not over the entire configuration space, because this distribution is defined only in the transition region. Now, this equation not only provides me with a workable equation, it's the analog of the Boltzmann distribution for reactive processes, but also tells me something quite important about the commuter itself. Before we go into that, let's look at this term a little bit further. So, very close to the reactant and very close to the product, M of t is very different from Boltzmann. It's actually much smaller than Boltzmann. Why is that? Because most of the time, when I explore configuration near the reactant, it's because I'm reaching out to the reactant and re-entering the reactant. It's just a wide fluctuations from the reactant. So the probability that I visit this point X because of reactive process is much smaller than it is at equilibrium. And this is taken care of by this thing. Similarly, when I'm in X, the probability to visit X along reactive trajectories is again much smaller than the Boltzmann distributions, because at equilibrium most of the time I visit X because of thermal fluctuation for the product. And this is taken care by this factor here. So it makes sense physically. That's what I'm trying to say. However, there is an important property that this equation is telling me, and in order to appreciate, so we need to define the concept of reaction coordinate. But let me first say that this equation implies that Q of x is an ideal reaction coordinate. But of course, we haven't defined a reaction coordinate, so I don't expect this sentence to be anything to you at this level. So what does it mean? Well, what is a reaction coordinate? A reaction coordinate is a very useful concept in chemical physics or in statistical mechanics. And you can think of the reaction coordinate as a one-dimensional manifold in configuration space that carries information about how a reaction is actually taking place. And by reaction, again, I mean structural reaction, right? Not necessarily a chemical reaction, actually not a chemical reaction for this problem. Now, suppose so you can imagine low temperature system tries to be in valleys and cross only when necessary, right? If I have a little energy, I will not fly over Bondone, I will cross the saddle point either at Rovereto at Arco to reach Lake Garda. But if I burn a lot of ITP or I burn a lot of gasoline through an helicopter, then I might cross the Bondone. So clearly, if I have a lot of energy, I have a large temperature, I don't care about barriers, and I move in straight lines. If I am very much low in terms of energy or temperatures, I try to stick on the minimum energy path. Now, if my system has a energy profile with, I don't know, something like this with a little barrier here, clearly, ideally, I have a one-dimensional manifold that carries me from the reactant and product. And chemists and physicists have been debating for decades of what is the concept, how to formalize this intuitive idea that if I want to understand how a reaction takes place, really a reaction mechanism is encoded in finding this one-dimensional manifold that tells me wherever I am, will tell me how far have I gone in the reaction. And the problem of finding a reaction coordinate is always far from trivial, right? For instance, suppose I have a reactant here, a product here, and an energy value made like a Z. Clearly, X and Y are not good reaction coordinates. Well, because, well, in principle, it is true that as I move from reactant to product, my Y decreases. However, my Y variable is not able to distinguish between two states. Sorry, between this state and this state, and this state and this state, and maybe here there are barriers. So by just looking at Y, I get a completely wrong description of the dynamics. Likewise, if I look at X, I get an even wronger description of the dynamics, because you see the dynamics proceed by backing track on X and then proceeding on X again. So what is the reaction coordinate? Well, first of all, since we're interested in slow reactions, in rare events, the reaction coordinate, well, first of all, since I'm interested in distinguishing reactor and product, the reaction coordinate must be an order parameter. That is a collective variable that is able to distinguish two states. Magnetization is a good reaction parameter for ferromagnetic transition, right? Or the parameter, because it's 0 in the paramagnetic phase and 1 in the ferromagnetic space, sorry, finite in the ferromagnetic space. So if I'm looking at a reaction that starts to demagnetize and then all of a sudden I switch on a magnetic field and I look at how this magnetizes, or I lower the temperature all of a sudden and the system spontaneously undergoes a ferromagnetic transition, then of course magnetization is a good order parameter. But in order to be a reaction coordinate, it must be the slowest variable in the system. Slowest collective variable in the system. What does that mean? Let's go back to our graph. We want basically that by the time the dynamics proceeds along two neighbor slices of reaction coordinates, all the orthogonal degrees of freedom have time to thermalize much faster. If you think about it, it means that the energy landscape is steep in all directions except this, because remember we had this exercise of understanding thermalization timescales for the harmonic oscillator, and the thermalization timescales was inversely proportional to the second derivative, or the Laplacian, or the determinant of deviation, whatever, the trace of deviation. I don't remember what it is in many dimensions. I think it's a determinant, but never mind. I mean, let's stick to one simple case, the curvature. Let's call it the curvature. So what I'm saying is that the steeper is an harmonic oscillator, the faster is thermalization scale. So this idea of collective variables being the value of the system in a multidimensional space correlates to the fact that anywhere I look, I'm in the flatter direction if I move along the reaction coordinate, and I'm in the steeper direction. So once again, the reaction coordinate to go from Trento to Garda is perhaps moving along the Adige Valley, where I'm basically flat, turning right after Mori, and crossing a little barrier to land into Riva. Because that's the direction where whenever I look, I see steep mountains, and the only direction flat is in front of me. There could be an alternative take through the other side, and therefore there could be a reaction that are so complex that involve more than one reactive channel, and each reactive channel has its own reaction coordinates. Let's not deal with those complications. I'm just trying to show for system where there's only one reactive channel, the reaction coordinate is the least steep directions I can go to. Which means that if I freeze my system to be in one of these configurations, the thermalization scale in the orthogonal configuration is extremely fast. The thermalization scale here is so fast. So if I constrain the system to be in a value of the reaction coordinate and I let the system to move freely in the perpendicular manifold, then it will thermalize almost instantaneously, which means that there is once again a decoupling of time scales between the time it takes to progress along the dynamics, along the reaction coordinate, and the time it takes to thermalize on the orthogonal directions. Now, with this idea in mind, this is the concept of perfect reaction coordinate we would like to have. And in 1D, it's obvious, is the dimension. In 2D, can still be worked out. Maybe if you're particularly strong, you can do that in 3D. But of course, doing that in ND is exponentially hard. But now we go back to the equations that we defined before. And now this is a multidimensional equation. Now let's look. Let's imagine that X is a point on an isocommuter's hypersurface. What is an isochrometer hypersurface? Is the same as an ergodic surface. The ergodic surface is an isoenergetic surface. An isochrometer surface is an isochrometer surface. And the chrometer is a hypersurface in configuration space which collects all the points which have the same value of chrometer. Now, on a restrict, so for instance, I don't know, if I were to draw plot, let's suppose these are the isochrometer surfaces. So that's, I don't know, Q equal 0.7, Q equal 0.9, Q equal 0.1, 0.5. I don't know. Now, this is the P1 half, Q1 half isochrometer hypersurface. Now, along all these points on the isochrometer hypersurface, the value of chrometer is constant. So, restricted to an isochrometer hypersurface, points are distributed according to Boltzmann only. Because this term here is constant. So this is telling me two things. The first thing is that reactive trajectories intersect isochrometer hypersurfaces in a point, and if I draw an histogram of these points, the density of points that I build up by histogramming the points intersected by a reactive trajectory on a hypersurface is a Boltzmann distribution restricted to the hypersurface. This is a highly non-trivial property which is exclusive of chrometer hypersurface. Take any other hypersurface, and the points that the reactive trajectory appears on this new hypersurface are not defined in a Boltzmann distribution on this manifold. So the isochrometer hypersurfaces are the only ones that are for which reactive trajectories define Boltzmann distribution. But then if you go back to the notion of ideal reaction coordinate, you discover that this is actually meaning that the chrometer is the ideal reaction coordinate because in the surface orthogonal to the chrometer locally, you're always Boltzmann, which means that you're always thermalized. And that was the notion, fast thermalization of the orthogonal direction. And by definition, the chrometer, you're always Boltzmann on the orthogonal direction if you are on reactive processes. So this is why the chrometer function is considered the ideal reaction coordinate. We conclude the discussion by looking at the reactive current. Now, the relationship between the reactive current, the chrometer, and Boltzmann is more difficult to obtain, and I will not do the proof. I don't think I even put it in the notes. It's possible to do it. It's just a little bit trickier because you have all these surfaces and moving across the surface and minus the flux backwards, and it's a bit of more intricate proof. There's a reference in the notes to lectures by Van Naden where he actually provides the proof. I would just quote the results. As in the previous case, the reactive current is proportional to the Boltzmann factor, but this time its direction is set by the gradient of the chrometer, which once again tells me that the probability flux occurs along the gradient of chrometer, which means that the chrometer is an ideal reaction coordinate, because the gradient of the chrometer is basically, if you pierce vertically hypersurfaces of isochrometer, you get the course of the reaction. So these three relationships together are the heart of transition path theory. The first relationship, let's summarize. The chrometer function obeys a backward Kolmogorov equation with zero eigenvalue. the second equation and the third equation. And I want to emphasize something that I already stressed at the beginning of the lectures, that none of this quantity depends on times explicitly. And by not depending on time, I have achieved this goal of having a purely phase space or configuration space dependent picture of reactive dynamics. Not only that, we also learned quite a lot of how to describe dynamics in terms of these stochastic descriptors. From the reactive transition probability density, you can get the rate as a flux along the surface of the product of the transition current. And you can imagine immediately that this has the right dimension. The commuter is dimensionless, is a probability. Well, fine. I don't think there's nothing to discuss in there. So I instead want to say something more and which tells us that these two stochastic descriptors, in principle, naively, we would say, why do I need two stochastic descriptors? After all, when I do Boltzmann distribution, I'm interested basically in the density of points. Well, I suppose I'm not interested in the rate. Maybe I don't care how long does a reaction take place. Why do I need the current? I mean, okay, the current gives me the rate, but if I'm only interested in understanding qualitatively how things change in time, maybe can I go along with MT by itself without having to specify JT. So what is the usefulness of understanding, of defining JT? I'll show you. To give you an idea, let's take this simple example. Suppose we have a reactant, suppose we have an intermediate and a product state in some, and suppose aside the intermediate there are two kinetic traps, T1, let's put it T2. What do I mean by kinetic traps? That if I look at that, there's like a barrier, an energy barrier that is like this, with a small barrier, a huge barrier, huge barrier, huge barrier, huge barrier, small barrier, a barrier, and a barrier. Okay, so once again, this is, I don't know, you can think of, let's say, Trento, Verona, Rovereto, and from Rovereto you can go to Riva, and from Rovereto you can go to, well, what's on the left-hand side? There's a valley that goes all the way to Vicenza. Yeah. Now, suppose we are interested in transition going from R to P. Now, since there are barriers here, reactive pathways can do this, spend time here, get here, and they will not be able to backtrack to R. They either go to P or to T2. We know they don't go back to R because they're reactive pathways. Now, even though this T1, of course, some reactive pathway will go straight from R to P, and other reactive pathway, according to our definition, will leave from R, go to T, and then to P. And any combination of there can be paths that go T1, T2, T2, T1, T2, T1, T1, T2, and then P, right? But in this case, T1 and T2 are kinetic traps. What do I mean by kinetic traps? That in order to go to P from R, you can, if you decide to go to T1 from I, then you have to go back to I before you can go to P. Similarly, T2. They are called kinetic traps. And kinetic traps are there every time. And I still use the example of protein folding. Protein folding takes forever. But it takes forever because most of the time you are in a maze and you get the wrong street. So proteins are like really people walking in a maze. They have to achieve a single structure, that's the product state. But most of the time they attempt to move. They end up in the wrong structure and they have to go back, open up, and retry. And then it's like being on a maze when you constantly get the wrong direction. And since they do things by chance, it's like trying to move the Kubrick cube by chance, hoping that every so often you get to complete the cube. Now the times it takes to complete the cube along by random move is exponentially long in the number of possible moves. That's why protein folding takes even minutes, although a typical move of a dihedral angle is a nanosecond. Nano, micro, milli, seconds, and so on. These are 12 orders of magnitude, right? And the reason, so suppose it takes you a second to do a Kubrick move, 10 to the 12 seconds is a long time, right? Now, if you look at the stochastic descriptors that we introduced, they carry information about this because the density distribution, the MT, will be large. Now let me use this. There will be some MT here. Well, this will be 0 because I'm in the reactant. The MT will be large here because the probability of finding the particle in the intermediate state along the reactive trajectories will be large. But it will be also large here and here because even larger than in I, because then maybe anytime you get to T1, you have really to wait until you find your way back. There's a narrow passage from T1 to T. So the transition path density tells you only where your transition path spend time. They don't tell you about productive, they don't tell you about what is the right path to follow to get to the product. They only tell you where people going randomly get lost most of the time. That's where they spend their time. However, if you look at the current here and here, let me use little vector to denote the current. I have current here, but the current in this direction is completely cancelled because anytime you have a flux from I to T1, you must get a backward flux exactly equal and opposite to go back to I1. So there's no current there. So what I'm saying is that if I were to draw the arrows of the vector field JT, they will be like this. So they will teach us about productive events. The current tells us how the mechanism works, while the MT tells us where you spend your time. And these two information are not the same. It's like on the maze, the current will only be finite along the solution of the maze. Think about the maze you get into in the last pages of your newspapers, right? Or your magazines, you have to play with maze. Then transition path density is wherever you try to draw your little scribbles to get into the product. And the current will only be 0 anytime you find regions that can take you to the product. So we see that these three stochastic descriptors provide very different information, which combined together exhaustively describes everything we need to know about reaction. We know the reaction coordinate, we know the productive events, we know where the system takes place, the spend times, and we know the rate. So basically, these three stochastic descriptors are what it takes to what it takes to describe a reaction. In this lecture, I've presented them as tools. I have not at all told you how to compute them. And this is an entirely different story. And much of the really tough research this year is devising algorithms to compute these guys without having to solve ergodic dynamics. That's one of the problems in my group we are particularly active on. This is the analog of developing Monte Carlo as an alternative to long molecular dynamic simulations. You know, a Monte Carlo is a way to sample directly the Boltzmann distribution without having to follow long time averages, right? And the advantage of doing Monte Carlo is that you can do global moves that take you away. You can forget about being a particle. You can really explore in a much more free way configuration space, and therefore converge faster with a Monte Carlo chain than you would do with a longer ergodic trajectory to equilibrium. Much research is being done in the field of statistical physics on how to access directly the description of transition path theory without having to do molecular dynamic simulations. And this is a field that recently is getting a huge attention because it turns out that machine learning is a very efficient way to do that, because you can learn from your past experience, for instance, you know, where regions of configuration space are likely to have given values of committers, and so on and so forth. In this course, I will not concentrate on these methods, unless perhaps in the last lecture I will provide you a couple of hints, but only on the main conceptual tools. But one part of this reason is that this is ongoing research, and every year there's some breakthrough in the field. So this is really at the front line of contemporary statistical mechanics, and it's likely that the ultimate solutions that will play the role of Monte Carlo in this problem is yet to come. We'll see in the following years.